We're going to return to a bit of calculus, the rates of change, that idea. Remember, a derivative is essentially a rate of change. But in some cases, we need to link a couple of rates together to come up with a solution. That uses the idea of, well, it goes by many names, the chain rule, implicit differentiation, whatever you want to call it. That idea, that dy dt is the same as dy dx times dx dt. We'll just look at some examples. We have a block of ice, and it's 10 centimetres, obviously by 10 centimetres by 10 centimetres. And it's melting, and those dimensions are decreasing at a rate of 1 millimetre per second. We want to know what the volume's doing. How's that decreasing once the edge gets to 5 centimetres? Let's pull this all together. There's my ice cube. I'll call the side length x. Dv dt is what we're trying to find. We've been told dx dt. It's decreasing, so I know it's negative. I've written it as a fraction. 1 millimetre is, of course, 1/10 of a centimetre. Dv dt is what I want to find. I know dx dt, so if I can come up with a relationship between v and x, we can create some sort of formula to substitute into. And of course, v and x are related. It's just the volume of the cube, which would be x cubed. So dv dx, 3x squared. So pulling that all together, we get our formula. There it is, minus 3x squared over 10. All right, now let's answer the question. We want to know what that is when the edge is 5. So x equals 5, substitute in, and there we have it, minus 7.5. But of course, we don't just leave the answer like that. They've asked us a specific question, and we answer what they're asking us. So, all right, well, I know the volume's decreasing at 7.5 centimetres cubed per second. Let's have a look at this one. A vessel in the form of an inverted cone, vertical angle of 90 degrees, and saying let the depth of that be x. We want to find the volume of water. So again, draw myself a diagram. Inverted cone, there's my water level there. We're saying the depth of that water is x. We want to come up with a volume for the water. I could create a right angle triangle there. They told me this vertex angle is 90 degrees. Therefore, I'm looking at my isosceles triangle 45 degrees. So that therefore means the other edge must be x as well. We know the volume of a cone, 1/3 pi r squared h. Substituting in, okay, we have the volume, 1/3 pi x cubed. Water's going to be poured in at a rate of 0.2 centimetres cubed per minute. We want to find the rate the depth is increasing once that water depth gets to 4 centimetres. So dx dt is what we want to find. We know dv dt, they told us that, 1/5. I've written it as a fraction. So if I can find something that links v and x together, but hang on, we just came up with an equation that links v and x together. So if I differentiate that, pi x squared, substitute in, I have a formula. Now let's solve the problem. So when x equals 4, we end up with 1/5 pi times 4 squared, 1/80 pi. Now I've left it as an exact answer. Depth is increasing at 1/80 pi centimetres per minute. Let's try this one. We've got a bubble. It's a sphere. Expanding, its volume is increasing at a constant rate of 70 millimetres cubed per second. We want to know what the surface area is doing when the radius is 10. Okay. So ds dt, I've called it, rate of change of the surface area. That's what we want to find. They've told me dv dt. Now in this one, I want to link volume and surface area, and that might not be immediately obvious. So actually, I'm going to use 3 derivatives for this one, because I can link surface area and radius together, and I can link volume and radius together. So I can then create ds dt out of all 3 of those rates. So volume, 4/3 pi r cubed, dv dr is 4 pi r squared. And find ds dr, and we get 8 pi r for ds dr. Substitute that all in, and I get a nice little formula, 140 over r. That's interesting. What's that telling me about when I'm blowing up a balloon? The rate of change of the surface area is inversely proportional to the radius. Imagine blowing up a balloon. You're blowing up at a constant rate. What does it do? You go, and the balloon expands. But as it's getting bigger and bigger, every time you blow into that balloon, it just doesn't expand by as much. Because it gets to that point where everyone goes, oh no, it's going to burst, it's going to burst. And you go, oh no, it hasn't burst yet. But yes, as that radius increases, the actual surface area is increasing at a smaller rate. let's solve our problem. We want when the radius is 10. So we get 14, and we have our answer. 14 millimetres squared per second. So we'll have a play with rates of change, 16A.